I am Dr. A. Anita, Assistant Professor of Chemistry, E.V. Vanniya Perumal College for Women, Virudhunagar. In this module, I am going to discuss about the elevation of boiling point. Before getting into this, we can recollect some of the factors we can discuss in the previous module, that is the lowering of vapor pressure. On continuing with that, in this module, we can discuss about the relationship between the elevation of the boiling point and the lowering of vapor pressure. Here, whenever a solvent is heated, the vapor pressure goes on increases. That is, we are taking the solvent on heating, on increasing the temperature, the vapor pressure of the solvent goes on increases. Well, as soon as the vapor pressure of the solvent reaches the atmospheric pressure, the solvent begins to boil. But when you come to the solution, dilute solution, and adding a little amount of solute into the solvent, then that solvent now becomes the dilute solution. On adding solution 1, the vapor pressure also increases, but here on adding the solute, the vapor pressure lowering takes place, so it consumes more amount of temperature in order to raise the vapor pressure. As soon as the vapor pressure reaches the atmospheric pressure, the solution 1 begins to boil. Similarly, the next solution, that is the solution 2, on adding some more amount of solute when compared to that of the solution 1. Therefore, here the lowering of vapor pressure has occurred to a greater extent. Therefore, it requires much more temperature than that of the previous one. So, as soon as it reaches the atmospheric pressure, the solution 2 begins to boil. Here, this is the graph representing the boiling point of solvent solution 1 and solution 2. Here we have to consider the BD and the CE. Both of them are parallel and approximately straight line. The triangle ABD and the triangle ACE are similar triangles. Therefore, the difference in their boiling point of the solvent as well as the first solution is called as the elevation of boiling point for the first solution, and the difference between the boiling point of the solvent and the second solution is called as the elevation of boiling point for the second solution. Here the AB and AC will be divided by AC is equal to AD by AE, as it is the rule for the similar triangles. The AB is nothing but the difference between the TB and the T1, and the difference between the BC is nothing but the TB and T2. That is, here an AD will be equal to the difference in the vapor pressure, and AE is also the difference in vapor pressure. From this, we can come to the conclusion that the elevation of boiling point is directly proportional to the lowering of the vapor pressure. Before getting into the next, we can come into the daily usage. Whenever you are cooking, you have to boil the water first, and then you have to add salt or rice something. After it gets boiled, then only we can have a lesser usage of fuels, or otherwise the elevation of boiling point is the phenomenon occurring here which consumes lot amount of energy. Therefore, there will be a lot usage of fuels in our daily household chores. Therefore, we have to boil the water first and then add the ingredients like salt or sugar into it in order to achieve its rapid boiling point. Here we can come to the conclusion that the elevation of boiling point is directly proportional to the lowering of vapor pressure. This is the relationship between the elevation of boiling point and the lowering of vapor pressure. From next, we can come to the point, how can you determine the molecular mass of the solute from the elevation of boiling point? As we have seen earlier, the elevation of boiling point is directly proportional to the relative lowering of vapor pressure. From now, we can make use of the Raoult's law. The Raoult's law, what's the Raoult's law? Like that the relative lowering of vapor pressure is directly proportional to the number of moles of solute and inversely proportional to the number of moles of the solvent. Therefore, here in the relative lowering of vapor pressure, we can write it as small w divided by small m, that is nothing but number of moles of solute. Whereas capital W divided by capital M, which is written in the reciprocal form, is called as the number of moles of solvent. Here, as we are taking the molecular mass of the solvent is a constant, we are ignoring the term capital M. And this delta T is proportional to the number of moles of solute and the number of moles of molecular weight of the solvent. Therefore, in order to remove the proportionality constant, we are multiplying it with the term ebullioscopic constant. It is otherwise called as the boiling point elevation constant or ebullioscopic constant or molar elevation boiling point constant, as the ebullium means it is the increase in the temperature or the boiling point elevation. Therefore, we can come to the conclusion that whenever the term W by M is equal to 1 and capital W will be equal to 1, then that delta T will be equal to the ebullioscopic constant. Therefore, the ebullioscopic constant is defined as the elevation in the boiling point delta T whenever this W by M will be equal to 1. That is, number of moles of solute is equal to 1 and the molecular weight, the weight of the solvent is also equal to 1. That is, 1 is nothing but 1 kg. Therefore, it can be considered as 1000 gram of the solvent. Therefore, the ebullioscopic constant is a constant which depends upon the elevation of the boiling point. Next, if you want to determine this small m, how can you find out? Here, the ebullioscopic constant is a constant term and it is the weight of the solute. We can measure it, and capital W is also the weight of the solvent. We can measure it, but what the term we have to measure it is the delta T in order to determine the molecular mass of the solute. For that, we are making use of the substance. Here, the formula tells us we are rearranging this formula in order to get the molecular mass of the solvent. That is nothing but 1000 into Kb into W divided by delta T into capital W. Here, the ebullioscopic constant has the unit of, here the delta T has the unit of degree Celsius and W has the value of unit of kg, and this W by M is nothing but the number of moles. Therefore, the unit for the ebullioscopic constant is degree Celsius kg per mole. This is the unit for the ebullioscopic constant. This ebullioscopic constant can also be determined from the thermodynamic parameters like latent heat of vaporization. The equation which relates the ebullioscopic constant and the latent heat of vaporization is given here. The ebullioscopic constant Kb is equal to RTB square divided by 1000 into Lv. Here R is the universal gas constant and Tb is nothing but the boiling point of the solvent, and 1000 is a constant and Lv is the latent heat of vaporization. The universal gas constant has the value of 8.314 joule per mole, and temperature, room temperature is 100 degree is the boiling point of water, that is nothing but 373 Kelvin. Here the value of the ebullioscopic constant for using water as the solvent is having the value of 0.52 Kelvin per kilogram. Next we can determine how to measure the measurement of boiling point elevation. Here, so there are so many methods to determine the boiling point elevation. One such important method is devised by Dr. Cotrell, a famous scientist. He made use of the Beckmann thermometer. Here, before getting into the Cotrell's method, we can find some of the advantages of the Beckmann thermometer. This figure represents the pictorial view of the Beckmann thermometer. It is entirely different from that of the normal thermometer. In the normal thermometer, the readings are from the 0 to 110 degrees Celsius or from 0 to 360 degrees Celsius with the temperature difference of 0.1 degrees Celsius, whereas in the Beckmann thermometer, it is called as the differential thermometer. We cannot find the original temperature using the Beckmann thermometer. We can find only the difference in the temperature alone with the Beckmann thermometer. Here it has the readings of from 0 to 6 Kelvin. Here the readings are marked in Kelvin scale, and the initial value is 0 and the final value is the initial value is the 0 Kelvin and the final value is the 6 Kelvin. Here the sensitivity of this thermometer is 0.01 Kelvin. Like other thermometers, it is also having a mercury reservoir at the top, and the temperature sensing area is having the bulb. Whenever we are shaking the thermometer, the mercury reaches its bulb regions, or on turning it that side, when you are shaking, it goes to the reservoir. This Beckmann thermometer has its important application in measuring the elevation of boiling point using Cotrell's method. Here, this Cotrell's method consists of 4 important apertures. The first one is the glass boiling tube with graduations in volume with the which can attach to a vapor phase condenser at its side arms, and it is having an inverted funnel with the 3-armed edge. Here, as soon as we heat, the vapor can go and it spreads along its 3 directions so that the thermometer can sense it easily. Here, the Beckmann thermometer, what we have seen here, is inserted inside the glass hood and it is placed inside the tube. Initially, we have to take the solvent, which is a known volume of solvent is taken in the boiling tube, and it is heated along with the porcelain bits in order to avoid bumping while it boils. Therefore, as soon as we heat, the vapor gets escaped and it goes through the narrow end of this and it can disperse through all its 3 arms. Therefore, the boiling point of the solvent alone can be measured using the Beckmann thermometer. After that, we have to add small amount of solute in order to make the solvent into a dilute solution. After that, when you are heating, after certain rise in temperature, the solution also begins to boil. Therefore, there will be an increase in temperature in the Beckmann thermometer, and as soon as it reaches the steady value of temperature, we have to record the readings. The readings we have recorded is nothing, it's not the temperature, but it's the difference in the temperature between the boiling point of the solvent as well as the boiling point of the solution, which is nothing but the elevation of boiling point. Therefore, on using the Cotrell's apparatus, we can determine the elevation of boiling point. Once the elevation of the boiling point is measured using the Cotrell's apparatus, we can determine the ebullioscopic constant. Ebullioscopic constant is a constant value. Therefore, we are measuring the elevation of boiling point using this Cotrell's apparatus. And what is the value? W is nothing but the solvent weight. The solvent weight can be determined from the value of the volume of solvent we have taken, and when it is multiplied with the density of the solvent, we can find out the weight of the solvent. Therefore, weight of the solvent can be determined. The ebullioscopic constant is a constant value, and what the amount of solute we have added into the Cotrell's apparatus after sometimes can be measured. On filling all this value, we can determine the molecular weight of the solute, and that is the aim of this work. From the elevation of boiling point, we can find out what is the nature of the solute. And once the nature of the solute is found out, we can find out how the influence of solute will have its impact on the elevation of boiling point, and which is the important colligative property which we have to find its application in various fields. In industrial sectors, it has its important role, like whenever a substance is to be heated, first the solvent has to be boiled. After that only we have to add the small amount of solute or any other substances in order to make it a fuel free or fuel less consumption environment. With this, we can come to the conclusion. In the next, we can find out we will discuss about the depression of the freezing point. And the points to be remembered here is, first we have to boil the solvent, and then only solute has to be added in our day-to-day life. And moreover, the molecular weight of the solute, whatever we can use, can be determined by the Cotrell's apparatus, and Cotrell's apparatus is also an important important instrument devised by the Cotrell in making use of the Beckmann's thermometer, thereby determine the elevation of the boiling point. The elevation of the boiling point is also an important parameter which we have to be apply in our day-to-day life. Thank you.